My name is Monty Veal. I'm representing the green team, the aerator mixer motor speed control system. Our members are Nicholas Tomadeski, Sarah Rogers, and TJ Hurlis. We'll go over a little bit of a background of the system and talk about the experiments we've conducted on our system so far this semester, which is the SSOC, step response, and the modeling, step response modeling. Background of the system, we're telling the motor what input power, we're giving the motor the input power and going into the aerator mixture drive system, which is basically the motor connected to a mixture blade, and the output control variable there is the drive speed RPM. Now, basically our system is similar to a wastewater treatment plant, which is in Chattanooga. What's happening is the motor is turning the mixture blades and it's mixing the oxygen that's coming into the tank. And what this does is allow the aerobic bugs that eat the waste to get oxygen, and this is due to EPA regulations and pollution control agency regulations. Also, the system has a 101 gear reduction ratio. Our SSOC, our operating range was 5 to 95%. The input power, we ran each experiment on 5% intervals, constant power input. We graphed the input versus output versus time. This is an example of one of the graphs. As you can see, constant input for this graph is 55%, and the output, which is the maroon line there, we took the average under the steady state of the output, and that was took 2 times standard deviation, 951 plus or minus 5.3 RPMs. We ignored the left portion of the graph because it's transient, considered transient startup, and we're concerned with steady state operation. Having taken the average of all the outputs and graphing them against the corresponding constant inputs, this gave us the steady state operating curve. And as you can see, it's a constant slope. So the slope of this line, since we're graphing output versus input, the slope is equal to the gain. And for our experiment, 17.5 RPM per percent. Next was the step response modeling. Our operation range was again 5 to 95%. We divided up into 4 ranges since we had 4 members in the team, stepping up 20% each time. We ran each experiment twice, so that enabled us to use a student T, and we approximated the FOPDT parameters off the graph, which is the gain, time, constant, time, or dead time. This is an example of the FOPDT step response graph. As you can see, we got constant input at 75% for a certain time, which is the time delay, and at that time we stepped up 20%, as mentioned in the previous slide, and it stays constant 95% throughout the rest of the experiment. The blue line represents the output, and to get the dead time, you draw a line through the slope of the output, and then draw a line across the constant input, and where that intersection point is from the time it takes for the system to respond to initial input is the time, the dead time, which is 0.1 seconds. And our time constant for this one is 0.18 seconds, and that is the time it takes the system to respond to 63.3% of the total output change. That was 1,500 RPMs. For the gain of the system, as you can see that the change 350 RPMs, and our step in input was 20%, so 350 divided by 20 is 17.5 RPM per percent, and that should be noted that that was the same as what the SSOC produced. Now, as far as comparing our up and down step values were the same, so we just took an average value for them all. And so our gain for step response was 16.9 plus or minus 6.9 RPM per percent. And our average dead time was 0.1 plus or minus 0.02 seconds. And time constant was 0.18 plus or minus 0.02 seconds. For the modeling, transfer function, there's what we used. Basically guess the parameters and graph them over the experimental data, and made it match the experimental data. Here's an example. You can see over here that the input experimentally it matches exactly the input theoretically, and same for the output. And for this, our average gain was 17.1 plus or minus 0.53 RPM per percent, and the average dead time was 0.12 plus or minus 0.01 seconds. The time constant was 0.2 plus or minus 0.01 seconds. So results, comparing the experimental and theoretical, you see that our experimental, the dead time was, average dead time was 16.9 plus or minus 6.9 RPM per percent. And for the theoretical, it's 18 plus or minus 2.9 RPM per percent. That's pretty close. And same for the dead time, 0.1 plus or minus 0.02, and then 0.12 plus or minus 0.01. And then for the time constant, 0.18 plus or minus 0.02, and 0.17 plus or minus 0.01.